Taking up the homework. Starting with question 1 here, we're asked to draw the following vector diagrams. So let's take a look at the original vectors first. So vector A, it's 10 meters to the right. Vector B is 20 meters to the left. Vector C is 10 meters up. And vector D is 5 meters down. So for part A, we're asked to find A plus B. So really, it's the resultant of vector A plus vector B. It is important to note that when you are drawing scale diagrams, it's really a good idea to consider doing these questions on graph paper. So what I'm going to do here is I'm going to pick a spot, and I'm indicating with a red dot its initial or our starting point. So vector A has a magnitude of 10 meters, and we're going to the right. In this case, we can do a 1-to-1 scale where 1 tile is equal to 1 meter. So when we start to draw, we just count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is our vector A. Now vector B starts at the head of vector A. And this time vector B has a magnitude of 20 to the left. So to make things go by a little faster, we start at the head of A, and we already know that back to the red dot is 10. So then we just have to go additional 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And this up here is your vector B. Now, as you can see, it's kind of hard to tell a bit, but if we just slide it along like this, you can see that vector B does in fact lie on top of vector A. So I just put them offset a tiny amount, and I'm moving the vector B label. And the reason why, it just makes it a little bit easier to draw the resultant. So we know that this first red dot was our starting point, and this last red dot is our finishing point, our end point. So the resultant is going to look like this. Now, of course, as I mentioned, I do like to have them as dashed lines. So I'm going to do a little bit of magical editing, and then I'm going to put it back in place. So this is the solution to part A. All right, let's tackle part B. So with part B, it's C minus D. So let's focus on that. So that's C there. It's 10 meters up. Now D is 5 meters down. But the issue is we're actually looking at C minus D. And as a reminder, for part B, the resultant is equal to C minus D is the same as C plus negative D. So what is negative D? Negative D is just equal to 5 meters, but in the opposite direction, which would make that up. Okay, so let's sketch it. So we're going to start off with vector C with 10 meters up. So we're going to go up 10 squares, and that is our vector C. And of course, at the head of C is where we attach negative D. And negative D was 5 meters up, and that is negative D. Zooming out a bit, we now can find our resultant, which is from the tail of vector C to the head of negative D. And of course, editing the vector, so it's a dashed line. And again, technically they should be sitting right on top of each other, but it's really hard to see what's going on. So I usually put them just slightly aside so we can tell which vector is which, especially when they're collinear. So that's part B. Next, part C. Okay, so next, let's take a look at this expression here. So we're trying to find the resultant of 2 times A minus 1/2 of B. So what we're going to do is we're going to do that down here, and then we're going to graph it. So let's take a look at what 2A is. 2A is equal to double of this. So that'll be just 20 meters, but to the right. Next, let's talk about negative half B. Negative half of B. Let's talk about the half first of all. So since B has a magnitude of 10, half B would have a magnitude, let's try that again. Since B has a magnitude of 20, half B would have a magnitude of 10. And since B was going to the left, the negative means that this is going to the right. And now we sketch. So there's our vector A, 20 tiles to the right. Again, we attach vector B to the head of vector A. And now we have our vector B. Our resultant starts at the tail of A and then goes to the head of B. And of course, we make the resultant a dashed line. Part D. Now we're looking for the resultant of vector A plus vector B plus vector C. Now things are a little bit different here. And here's the reason why. A and B are along the x-axis, but vector C is along the y-axis. These vectors are not going to be collinear. So what I'm going to do here is I'm going to cheat. In part A, we already had the answer to vector A plus vector B. So for the sake of convenience, I'm just stealing that diagram. So now what I'm going to do is I'm going to take my vector A, which is 10 to the right, add my vector B, which was 20 to the left. And now we have to add our vector c. So our vector c is 10 meters up. Okay, so I've sketched vector c to the side here. Now, where do we attach vector c? Again, it always goes in order. So A attaches to B and B attaches to C. So the head of B attaches to the tail of C. And our resultant always is at the tail of our first vector to the head of our last vector. And there's our resultant. Now, finding the length of this resultant, as you can see, is going to require something different than just straight addition and subtraction. And you can sort of see where we're going with this. Because if you take a look between this part on the x-axis here, just this little section, and this part on the y-axis here, you see we kind of have a little right angle triangle there, don't you? So we're going to get into this, how to solve this in the next couple of questions here. Okay, moving on to question 2. Question 2, we're asked to solve the vector equations in one mathematically. So we're not going to draw it, we're simply just going to solve it. Now, reminder, there are separate rules for collinear versus non-collinear vectors. Let's start off with part A. Part A, we're looking for the resultant of vector A plus vector B. So when we take a look at vector A and B are collinear. They're both along the x-axis. Therefore, we can just use positive and negatives to represent the directions, dropping the vector notation. Vector A has a magnitude of 10, but it is to the right. That makes it positive 10 meters. And again, it's positive because it's going to the right. Plus vector B. Vector B is to the left and it has a magnitude of 20. So therefore, that's negative 20.0. Positive 10 plus negative 20 is negative 10 meters. Therefore, the resultant is equal to 10 meters to the left. Again, note the negative sign was converted to this direction here. No negative sign in front. Part B, the resultant of vector C minus vector D. Vector C and vector D are both collinear to each other. Vector C is up, vector D is down, so they're both on the y-axis. That means, again, we can just use positives and negatives to represent their direction. So let's take a look at vector C. Vector C is 10 meters up. That makes it positive 10.0. Vector D is 5 meters down. That makes it negative 5. So if we look, we've got positive 10 and a negative makes a positive, so positive 15. Therefore, the resultant is equal to 15 meters up. And as a reminder, that positive is reflected in that direction up there. Part C, we're looking for the resultant of 2 times A minus 1/2 of vector B. Again, vector A and B are collinear because they are both on the x-axis. So we can just use straight up addition, subtraction, and multiplication to do this. That's going to be 2 times positive 10. Now, you don't always have to put in all the sig figs here. You could just write it as 10 in these interims. You just have to make sure they have the right number of sig figs at the end. Minus 1/2 bracket negative 20. And again, this is important that you get the directions right. Positive because we're going to the right, negative because we're going to the left. R is equal to 20 plus 10, positive 20, I should say. That makes that positive 30 meters. Therefore, R to the correct number of sig figs is 30.0 meters to the right. Taking on part C. Part C is when things get a little bit more complex. As mentioned earlier, vector A and B are collinear to each other. They're on the x-axis. But vector C is on the y-axis. That makes this question a little bit more complex to solve. So what we're going to do here is we're going to grab that vector diagram that we did in part A. And of course, by part A, I meant to say question 1. So part C of question 1. Here is that diagram. As you can see, we've got a resultant here. But what we don't know are the length of the sides of this hidden triangle. And that's this one right here. What you can see is I've kind of drawn a little shortcut here. See, we know that vector A first goes this way, and then vector B backtracks. But if we combine A and B together, that result, notice the word result, is just this little vector here. I'm going to call this vector here, I'm going to call that vector X. And I'm going to call this one, we know that it's already called C, but for the sake of consistency, I'm going to call that vector Y. You can probably guess why I'm calling them vector X and vector Y. Vector X is on the x-axis and vector y is on the y-axis. Logically speaking, and let's take a look at the numbers, we know vector A was positive 10, and we know vector B was negative 20. So that makes vector x negative 10. How did I get negative 10? Well, I took A plus B. 10 plus negative 20, that's negative 10. And vector y is pretty easy because it's just the same as vector C. And it's positive 10 because it's going up. So to solve this question, we actually have to find both the magnitude of r and this angle theta here. Since we have a triangle, we're going to have to use trigonometry. But the nice thing is we have a right angle triangle. So therefore, we can find the magnitude of r using Pythagorean theorem, which in this case is the magnitude of r, which is the same as our hypotenuse because it's opposite the 90, is equal to the square root of the magnitude of vector x squared plus the magnitude of vector y squared. Dropping the extra notation, r is equal to the square root of x squared plus y squared. Now we can substitute in. Notice I didn't put a negative sign in front of the 10, nor did I put a positive sign in front of the second 10 here. And again, the reason why is because these symbols mean magnitude, which means no direction, just the actual amount or length of it. We'll deal with the direction later. So this is equal to, now most of you would just square this, get 100 plus 100, so you get 200, and take the square root of 200. But I'm going to show you something else. This is the same as 2 times 10 squared. Now the reason why is because I can take the square root of everything when it's like that. And the square root of everything, that would be the square root of 2 times 10, or 10 root 2. As mentioned before, I like to have the most precise answer I can get. However, the actual calculated value would be 14.14 meters. Now, that's just our magnitude. The next thing we have to find is our angle. So finding theta. So again, we have a choice to make. Let's take a look at the values on both sides. So here, we know that is going to be the magnitude of that side is 10. The magnitude of this side is 10. That's based on the given amounts. We also know the resultant, but there is a potential again with the resultant that we could have made a mistake. Even though if we use this answer here, there will be no rounding error, but we could have actually made a calculation error up above. So again, as best practices, use tangent. So tan theta is equal to the opposite over the adjacent. I'm not going to make you write this step every single time, but I will make you do this one. The opposite is the magnitude of y over the adjacent, which is the magnitude of x. So from now on, start here. Isolating for theta, we take the tan inverse or arctan of y over x. I've dropped the excessive notation, and now we know that y and x are magnitudes. So that's going to be 10 over 10. Theta works out to 45 degrees. And now we can write our conclusion. Therefore, the resultant is equal to 14.14 meters, and that would be left, because that's pointing to the left, 45 degrees up, and that's all there is to it. Finally, let's move on to question number 3. So in question number 3, we're dealing exclusively with non-collinear vectors. So for part A, r is equal to vector A plus 2c. So in my approach with doing these questions, especially when we're first starting out, is immediately I'll take the value c and then rewrite the expression as 2c, like this, and then create the scale diagram based on that. So we know that 2c has a magnitude of 20, and it's moving up, and a is a magnitude of 10, and to the right, which is reflected in our diagram. A is 10, and c is 20. In this case, you can see that we have just a simple, straightforward right angle triangle. But to make things a little easier for us, I feel that it makes most sense if we still label these axes x and y. And the reason why, because it makes more sense when you have to plug it into the Pythagorean theorem. 2c is less obvious. So vector x basically just represents what the final result is in the x-axis, and this vector y represents what's the final vector, the overall vector in the y-axis. In this case, vector y is equal to 2c. So solving for r, we use Pythagorean theorem. R is equal to, I should say the magnitude of r is equal to the square root of the magnitude of x squared plus the magnitude of y squared. Substituting all that in, we get 10 root 5, which as a decimal is 22.4 meters. Next, we find the angle. We're looking for angle theta, And again, we're going to avoid using the magnitude of r in this case, because with the magnitude of r, we could have made a mistake in that calculation. So we're going to stick with the original data, which is the values for side x and side y. So tan theta is equal to the magnitude of y over the magnitude of x. Magnitude of y, of course, being the opposite side, and the magnitude of x being the adjacent side. Isolating for theta, we get tan inverse, or arctan, of 20 over 10. Theta equals 63.4 degrees. Therefore, the resultant is equal to 22.4 meters right, 63.4 degrees up. And as a reminder how we got that, if I was to redraw the resultant, the resultant starts here at the tail of A. And we know we went this way first towards A, and then we moved up to 2C. So as you can see, our vector goes right, and then it swings up like that. Therefore, right, 63.4 degrees up. Part B. Part B, we're looking for the resultant of vector B minus vector D. And again, subtraction is the same as adding the negative. So on my little aside here, I've taken our vector D and I've rewritten it as negative D, which simply means that instead of going down, we're going up. So negative D is up versus D, which is pointing down. Following the order, we start with vector B, and then we add our negative D. So that's 20 meters to the left, followed by 5 meters up. And again, for the sake of clarity, we're using this x and y vector notation here. Next step is to find both the magnitude of r and our angle. Focusing on the magnitude of r, the magnitude of r is equal to the square root of the magnitude of x squared plus the magnitude of y squared. X squared, the magnitude of x, I should say, is 20, and the magnitude of y is 5. Now again, as a reminder, we didn't include the negative and we didn't include the positive because we are just working with the magnitudes. That works out to 5 root 17, or as a decimal, 20.6 meters. Finding theta, again, tangent. And the reason being is that we could have always made an error when calculating for r. So we're going to stick with side y and side x. In this case, since theta is over here, the opposite side is y and the adjacent side is the x. Tan theta is equal to the magnitude of y over the magnitude of x, which is equal to tan inverse, or the arctan, of y over x. Therefore, we get theta is equal to the arctan of 5 over 20. Theta is equal to 20.6 degrees. In conclusion, and again, when in terms of the direction, notice we go to the left first and then we went up. So the order when we report our angle, it's going to be left, then up. Therefore, r is equal to 20.6 meters left, 20.6 degrees up. And finally, part C. With part C, we had one of the more complex equations here. 2a minus 4c plus b minus 2d. The only vector that is unchanged from its original is vector b. So again, as best practices, on the aside here, we're going to figure out how much 2a is, how much negative 4c is, and how much negative 2d is. 2a is equal to 20 meters to the right. Negative 4c is going to be 40 meters down. And again, the negative flips that direction, and the scalar quadruples that amount. And then negative 2 times d. The negative takes that down, turns it into an up, and we're doubling the value for d, which is 10 meters. Now zooming back out, because this is a rather large scale diagram, what you should be able to see is that the x-axis information vector, the x vectors, I should say, cancel each other out. And if you notice, 2a is 20 meters to the right and b is 20 meters to the left. They're opposite to each other. They will cancel. In the end, we get a resultant of negative 30. There has to be an easier way to figure this out. And yes, there is. And in fact, we could actually figure this out without actually having to draw the diagram. So here is the easier way. Let's take that original expression, that original vector equation. R is equal to 2a minus 4c plus 2b minus 2d. And then let's take a look at which axis each of these vectors are on. This first vector, the 2a, that's on the x-axis. The c vector, negative 4c, that's on the y-axis. Our b vector is on the x, and this negative 2d is on the y. So what we're going to do instead here is we're actually going to break this whole expression up into two equations. One that just works on the x-axis and the other that works on the y. So for the ones that work only on the x-axis, I'm going to call that r subscript x. And everything that's on the y-axis, I'm going to use r subscript y. R means resultant, but the subscript x means just the resultant for the vectors on the x-axis, only the x-axis vectors. And ry means the resultant of just the y vectors. So rx is actually equal to 2a, because that vector was on the x-axis, plus b. And then over here on my ry, that's negative 4c minus 2d. And don't forget your harpoons. Now, because of this, by doing this, these vectors are collinear to each other because they're on the x-axis. And these two vectors, they're on the y-axis. So we can actually just do simple addition and subtraction to solve these ones when they're in this form. So dropping vector notation, rx is equal to 2 bracket. How much was a again? Well, a was 10 meters to the right, so that makes that positive 10, plus the magnitude of b. My apologies, magnitude and the direction of. So b is 20 meters, but to the left. That makes this negative 20. Rx is equal to 20 minus 20. Rx is equal to 0. Therefore, our resultant in the x-axis is what we call the 0 vector. So it's just 0 with that little harpoon because it's technically a vector still. And the reason why we write it like this is because every vector needs a direction, but literally with 0, you can go in 0 meters in every direction. There is no single direction associated with it. Next, let's focus on ry. Ry is equal to negative 4 bracket. Well, we have to see what c is equal to. Well, c is 40 meters and it's, let's try that again. This is c and it's 10 meters and it's up. So c should be positive 10, minus 2 bracket. Let's figure out what d is. D is 5 meters and it's down. So that should work out to negative 5. So ry is equal to negative 40 plus 10. Ry is equal to negative 30 meters. And since rx is equal to 0, our resultant, or an actual resultant, is going to be our resultant in the x plus our resultant in the y. And normally, this would make a right angle triangle because the x-axis is perpendicular to the y-axis. But since this is 0, our resultant is just equal to whatever ry is, and therefore r is equal to 30.0 meters down. And there you have it. In the next video, we're going to explore more of these non-collinear vector equations. But we're going to get into the ones that are more complex. Specifically, we're going to get into the ones that also involve using sine law and cosine law. Those ones are significantly more challenging, and there'll be other techniques that we need to work with.